So OpenRocket is an application which we use to design and simulate our rocket in. It'll tell us really whether our rocket is going to be safe enough to fly. So the first thing we'll do is with OpenRocket is just change the units. We'll have all our units in millimeters in the metric system. The only unit that is not in the metric system is distance, and that's because altitude is measured in feet for aviation, and so we need to know the altitude above ground in feet, not in meters. So you can change that by just going to distance and changing it to feet, and everything else will keep it as default metric. Some people like to have acceleration in G's or in meters per second squared. It doesn't really matter. Now, OpenRocket has three main areas. One is this area here, which will form a bit of a branch-like tree system. It will have all the components of our rocket as we make them up. This section over here has all the components that we can add to our rocket, and we select each component as we go. And down here we get a visual representation of what our rocket looks like. Then when we change tabs up the top, we can add different types of motors to our rocket, and finally we can simulate the flight, and it can give us all the information that we need. So we'll begin by I like to start at the top of the rocket. So we'll begin by adding a nose cone. So with the nose cone, there's going to be a whole lot of different shapes which you can choose from, and that's selected via this top-down window. You'll have to do a little bit of research to look at what shape that you want to use for your particular rocket. I'm going to choose the Hake series, and I'm going to make it just slightly a little bit longer. Now the base diameter is really going to be the diameter of your tubes, of your actual rocket tubes, and in our case it's 60 millimeters. And this wall thickness, I'm not going to say it has a wall thickness, I'm going to say it's filled, and that means it's going to be solid. And we are 3D printing these. They are going to be solid. The next part we need to change is the component, is the material that the component is going to be made of. Now our nose cone is going to be 3D printed, so it's not going to be made out of cardboard. It's going to be printed out of PLA. This really gives us a bit of a density value to try and work out how much the component is going to weigh. If we can also change the finish that's on it, and that will determine a bit of a drag coefficient to help OpenRocket determine what your apogee is actually going to be. So I'm going to say we're going to paint this one nice and smooth. And if I click set for all, that'll set it for everything that we deal with. The next thing we're going to do is add a shoulder. Now the shoulder is the part that slides into the actual rocket tube. So that diameter is going to be the inside diameter of your tube. And our tubes are roughly 2 millimeters thick. So that means this will be roughly have a diameter of 56 millimeters. And the length, again, this is something you will need to look up what to do. And you can find that in the Make High-Powered Rockets book that's been assigned. And I'm just going to say that length is about 60 mil. And again, I'm going to end cap this because it is going to be solid. Now we've set a limit for this class for the mass, and the maximum mass we want a nose cone to be is 150 grams. And that's really because if you have a nose cone that's close to half a kilo like this one here, it's going to do some damage, and it might even snap a shock cord. So we'll change the print infill to make sure it comes out as close to 150 as we possibly can. So once you're finished and you're happy with all of that, you can just click OK, and I'll zoom out a little bit here. And there we go, and now you can see the nose cone there. If you ever want to edit that, once you've changed it later on, you can just double click on it there, or you can highlight it and click edit over here. So now the next thing we're going to add to this is the actual body tube. So we'll just click body tube, and you'll notice straight away that it's automatically given us an outer diameter and an inner wall diameter. It's given us that based on the nose cone. It wants the two to match up nice. So OpenRocket's smart like that, and it helps us a lot as well. Now the length of the tubes we're giving you is roughly 600 millimeters. So I'll put that in there. And it is also cardboard. If we go over to this, the motor, this component a motor mount? Does that mean, is this the part that the motor is going to be held into? And no, it is not in this particular case. And override, we can override the mass. Now 140, 150 grams is about right for the tube. But when you weigh it, you'll add in the actual weight of it. And I can click OK with that. And I'm not sure why this is not continuously updating. There we go. Now the next thing we want to add is the motor mount, is that tube that is going to hold the rocket. Now with the body tube selected, we click on inner tube, and the inner tube is the motor tube, and you'll notice now it's created a tree saying that the inner tube is inside that body tube. The length of these tubes you'll have to measure because everyone's is going to be slightly different, but they're roughly 150 mils. The wall thickness is going to be about 2 millimeters thick. Now the inner diameter is 29 mil. Unfortunately with OpenRocket, if you change this, it doesn't change the outer diameter. So you have to change the outer diameter, and the wall thickness will come off to do this. So 29 plus 4 is 33, and that should automatically update it to 29. Okay, it is going to be made of cardboard. We stick these out a little bit. Now you're going to have to measure how far you're going to stick that out the back. Everyone's will be different, but it's something you can determine later when you're doing your build. If we click on motor, this component is a motor mount, so we'll leave that. We are not doing a cluster rocket, and we don't need to worry about anything else except the mass. But for now, we'll just leave the mass and just make it a nice number. And then we can add that. Now, to fix the motor mount to the actual tube, we need to add these centering rings. Centering rings are a donut shaped, and they'll keep the tube well centered in the rocket and also secure it in place. So what we do is we then select the body tube again, and we go centering ring. Now again, the OpenRocket is smart. It knows the outer diameter of it and the inner diameter of both circles, and that way, based on the inner tube and on the main rocket tube. Now they are a slightly bit thicker, so you'll have to add thickness again. Now again, these are going to be 3D printed, so whatever you selected for your 3D print, make sure you select it for this one as well. For now, I'm just going to put this about in that position. We will change that later on, and we'll override it. And I know from a fact these are very light, so we'll go OK, and we can add that. Now, so we don't have to do that again, I can just click it once and click duplicate, and then if I double click on it, I can now slide that a little bit more forward. So now I've got my two centering rings, which are going to hold my rocket in, hold the inner tube inside the to the main tube. And this is really where it transfers the thrust of the motor to the actual body tube. Okay, so now we are going to add some fins to the rocket. So there's three options to add fins in OpenRocket. There's trapezoid, there's elliptical, and then there's freeform. So trapezoid is really just a four-sided shape with two of the sides being parallel. Elliptical is a semicircle, and freeform means you can make any shape you want. And I'll just quickly show you with freeform. What this allows you to do is it gives you the shape, and you can just click and you can add and you can change the shape of it and put it wherever you want. like that, and then you can make up your fins like that. I'm not going to do that. I'll let you play around with that. I'm just going to add some simple ones, and I'm going to just add trapezoids. Now, I would recommend that you really think about the size of these when you do it, and have a look and even draw it out on a bit of paper. But you can see here it's given us a default of 50 mil. Now that's 5 centimeters, and 5 centimeters is very tiny. These are going to be 3D printed, so 5 centimeters will break. So we need to make them a little bit bigger. And so I'm just going to make them all an arbitrary number, like that. And that's a pretty good size. I might just move them a little bit. I like to have them a little bit more centered like that. There we go. If you want to get an exact number, you can just click in there and type it. They're not going to be cardboard. They're going to be PLA because they're going to be printed. We do want 3. The thickness, now the thickness of them. We had a team do 2 mil last year. I think they might have snapped. 3 mil is kind of the norm and the standard go-to. We did have another team do 4 or 5, and I thought they looked pretty good. They were nice and chunky and big, but the heavier you make it, the lower your stability it's going to be, and also the lower your apogee. So you're going to have to play around and make up a decision. Now the fin cross section is really the area that strikes the airflow. So I'm going to round this to make this nice and to make it a nice curved surface. I don't want airfoil, I want rounded. You can add fillets to it if you want, which you will be adding fillets to, and you will probably add about a 1 centimeter fillet on the outside. Now also, I know the mass of these are pretty light, but we'll just say it's a total mass, so we'll say about 60, and that's about 20 grams each. Now fin tabs. So fin tabs is what glues our fins into the rocket. So once I show you, once we start making these long enough, you'll see that these here, the fin tabs will go down and they will be glued to your inner tube, and the centering rings will be epoxied to the sides here. So your fins are kind of sandwiched into that position by and held in with epoxy. So you can change the depth, which you're going to have to calculate, because the depth is going to be the difference between the outer diameter of your body tube and the outer diameter of your inner tube, and that's the depth you're going to want. The length, do not make them bigger than your fins, but also you don't want to make them small, because they are what holding your rocket, your fins, sorry. So they'll just break and your fins will come off and it'll be all over. So make them a decent size. Usually having about 1 centimeter either side is a good number. So if I make that 60, that works well. And we can leave it in the middle, or you can move it like that, but I don't really feel that's necessary at all, and you're just making things a little bit complicated for yourself. Again, there's this calculate automatically, so if I do that, it'll work out the depth and also the length, but I don't like that length, so I'm going to change it, and I'm going to do that. Oh, sorry, 60 like that. If you decide you don't like this shape anymore, but this is a good starting point for you, if you click convert to freeform, it'll convert it to that freeform option, and then you can play around just like you want. Later on, as we move down our build, and once our fin design is completely finished, and we want to make sure the design of the fin is finished, you'll hit split fins. So when you hit split fins, it breaks it up into three different components. That way you can add an individual weight for each component, because they will be slightly different because they're being 3D printed. But also when you export this as an object for printing, it will only export one fin, where if you don't split them, it'll export them as 3 fins, and there's a lot of playing around you'll have to do in order to get it to the one fin. Okay, so now that our fins are in position, what we'll do now is we'll just make the centering rings touch them, because so I actually didn't get the numbers, but you will have to calculate this correctly. So that was pretty close. So this might be, this might be about, I think I made them 3 mil thick. No, I must have made them a little bit longer than that, fatter than that. There we go. So that's that position there put in, and now the top one. Ideally, you want to calculate this and you want to make sure you get it right. There we go. So that's pretty good. So now that's all in a good position. I do think these fins are a little bit too small, and I think they should be a little bit larger, just for just to avoid them breaking or anything like that. Okay, now we've got that on. Let's add on a motor mount, a motor retainer. So the motor retainer is the part that's really just going to stop the rocket from falling, the motor from falling out when it's sitting on the pad. So to do that, I'm going to select my inner tube. I'm going to select my inner tube, and I'm going to add a mass component. It is not an engine block. An engine block is something that's slightly different. So I am going to add in a mass component. Now with a mass component, you add whatever parameters you want. So the mass of these, I'm not really 100%, but that looks pretty good. I'm going to say it's the length. I think that length is pretty good. The diameter, it's slightly larger, and now I'm going to say it's at the bottom of the component, like that. And I think that's pretty good. That's looking good. That's roughly where it'll go. It might stick out a little bit more, yeah, about there. And being a mass component, we will change the name because we'll have a few mass components. So I'll change this to motor retainer. Make sure you do change the name, because if you don't, you'll have all these mass components and you won't know what any of them are, and I won't know what any of them are. Okay, so the last thing we need to add for the outside of the rocket is some launch lugs. Now, they go on the body tube. Now, OpenRocket gives you two options. One is a rail button. So I might just add one rail button so you can have a look, and I'll change the view. So you can see it's just a button that goes on the that goes on it, and that's what the tower, that's what the rocket slides onto in the tower. We have kind of a, because these are only really good if you're screwing them in position, but we're going to be gluing ours in. So for us to glue ours in, we've actually designed some which are quite long and elongated, so we can't really use rail buttons to accurately represent it. We could potentially use a launch lug, but if you look at what a launch lug does, is I'll just add one there. Sorry guys, I've just got to close something which it opened up. If I add that launch lug there, you'll see, if we go back view, you'll see that it's got a big hole in the center, and this is because in a launch lug is used on a different type of launching system, and it's really just a metal rod that guides the rocket straight up. You could potentially use this to represent it, because all we've got to make sure is that the masses are accurately represented, the size is represented, to give that component a pretty good center of mass. So when OpenRocket uses that to look at everything else, it'll treat that it'll treat it exactly the same. But I'm actually not going to use that, and the reason I'm not going to use that is I'm not sure how much that will affect the OpenRocket's flight performance, because it does have a hole in the center and ours are solid. So I'm going to remove that, and I'm just going to use a mass component. So I'm going to use a mass component. I know they're very light because they're very small. Their length is about that. Sorry, their lengths yeah, about 25, but their height was only about 10. So there's something like that. Now I'm going to change this to launch load. Now you'll see here that this is put it on the inside of our rocket in the middle. We need to change that. So we're going to go to radial position. I want it down the bottom of my rocket, down the very bottom. And also I want it on the outside. So this is a 60 mil tube. So if I put 30 mils, you can see that it's halfway. So we just so we need to go 30 plus, what do we say the diameter is 10, so roughly 35 should potentially do it. There we go. So now it's on the outside of our rocket, and if I just show you now, I'm hoping that I got it right. Yep, I did. I know this says it's a circle, but it actually treats it as a solid component. So let's open that back up. Let's change its position. Their position is important. It's something you'll need to read again. But I might just put it just here. I'm going to leave its radial position, its override, its appearance. One thing I will do is I might just do this, is I might change that to 0. I might just offset it just a little bit. And I'll show you why I've done that. If I have that at 0, and if we put this now on back view, when we put our rocket on the launch rod, it's going to hit the fin. So we're not going to be able to get our rocket onto the launch tower. So determining where that goes is important. We have 3 fins. This one here is at 0 degrees. So we need to put it completely opposite that at 180, and that's going to give us equal distance between the other 2 fins. So I'll go back in here and I'll change it to 180. There it goes. All right. Okay, let's change that back to side. Now we have 2 of them. If we had 1, it will fall off. So we'll duplicate it. I'll grab that. And this one should go nice and low on the rocket. So about there is pretty good. So I'm happy with that. Now the outside of our rocket is complete. So now we need to look at how we're going to get the rocket back to the ground safely. And we're going to be using a parachute for this. So the parachute goes in the body tube. We're going to add a parachute. Okay, we know the package says it's an 18-inch parachute. So what I can do is this individual item I can change to inches, and I can change that to 18-inch, and there's our parachute. The drag coefficient, you can try to look up what it is. Some are higher than 1, some are significantly lower. So have a look, count how many shroud lines you have and the length of those lines, and also have a look at the what type of cord it is. Is it an elastic cord, or is it maybe a nylon cord? We're going to deploy this at the first ejection charge of this stage. There's not going to be a time delay. Its package length is going to be how small we're going to wrap this up when we put it inside the rocket. 2.5 centimeters or 25 mils is quite small, so I'm just going to make it a little bit longer, and I might make it a little bit fatter, and to give us a bit of a realistic impression. We should be able to get it a bit smaller than that. Should be able to get it about there. They are very light, but I'll leave this one as default. Once you weigh it, make sure you put in the accurate mass. Something. There we go. Now where to put the parachute for the rocket. I like to simulate things for worst case scenario. So if I leave it up the top like that, then that's going to give me a high stability. If I move it down the bottom, it will reduce my stability slightly. So I like to go off worst case scenario and say, well, my stability is going to be lower as a result, and the parachute is going to fall down at launch no matter how I tie it up. That's an assumption I'm making, and it seems to work for me. Now the parachute is protected because the ejection charge is a hot charge. So it's protected by a Nomex cloth. So I'm going to add here Nomex cloth, and this is really just something that's made out of a material like a firefighter's suit, and we wrap the parachute in it. So what I'm going to do is I'm going to move that down to the bottom like that. I'm going to make it a little bit longer and a little bit wider, and that's kind of showing the and that's kind of showing that is wrapped around it. And these have a little bit more of a weight, not much, but I might get actually I can just do this. I'll call these I'll say these weigh about, oops, that's a bit too heavy, about 10 grams. They could weigh a little bit more. I'm going to change the name to Nomex cloth. And that's pretty good. We're just going to leave that there like that. Okay, now we've got to add a shock cord to connect the nose cone to the rocket. Now this shock cord is connected to both the nose cone and the main part of the rocket, because it'll be epoxied to the inner tube. Because the nose cone comes off at apogee, we don't want that to fall down without being attached to anything. So there's really a few ways you can represent a shock cord. I know the length of these shock cords are going to be quite long, and I know the mass, of them is going to be a little bit more than that. I'm just going to say about 50. Now, you can say that, well, it's going to go from the nose cone, so we'll just move it from the top of the nose cone roughly there, and it's going to go all the way down to about there, and it doesn't take up much space because it's only a 2mm elastic cord. You will need to measure yours to confirm it is 2mm, and it is in fact elastic. Some people I've seen have put the entire mass in the center of, in the middle of these two positions, and that's perfectly fine as well, because what we're trying to do is really just take into account that weight and the moment that will have on the actual rocket. I'm going to leave this one just like this. And there's our rocket. So it just needs one more thing, and that is a motor. So the motor over here, we're going to go new configuration, which popped up in another screen. You're going to be flying the G77. Now RMS means reloadable motor system. We are not using a reloadable motor system. We are using a single use motor. So I'm going to collect the single use, the SU. And you'll see it's got 4 or plugged. We're not using plugged, and we're definitely not using 4. Now that means it'll take 4 seconds from when the motor finished burning till when the ejection charge is going to go. It has a time delay in it. We're actually giving the team the class 14-second ones, and if you need it to come out a little bit earlier, we can take off seconds, so we can shorten the fuse to make it less. So I'm going to add that, and you'll notice that it will now add a rocket into this section over here, and it will say G77R-14, and that's what our rocket is. You'll also notice now the stability has dropped a little bit, but it's given us a good stability of just over 2. Keep in mind that at this stage of the build, we want the class to have a stability of 2.5, and that's to account for changes that occur as the build goes on. Our apogee is about 2,000 feet, and we're going to hit about 16 Gs, and that's pretty realistic for this type of rocket. Now, if we come over to flight simulation, there is a few things we need to do over here. We need to go to edit simulation. You need to find the latitude and longitude and altitude of the Serpentine launch site. You can change your wind speed in here, so if you want, you can look up at roughly what wind is. We don't fly in extreme windy conditions, so we don't need to go too crazy. Our angle is straight up, and our launch rod, we have a few different launch rods at Serpentine, but we'll factor it on 2 meters. There are some that are about 1.5 meters long, and there are ones that are a little bit longer. But 2 meters is going to be pretty good. And if you're right on the margin, you can drop down your length to 1 meter, and we can just make sure it's still going to be safe to fly. So for right now, I'm just going to click OK to save all of that, and then I'm going to go run simulation. So that turns green, meaning the simulation's current. The tick means it's done well, and all of these parameters are good. So our velocity of the rod is the velocity of the rocket once it leaves the launch tower. And we want that number to be above 15 as an absolute minimum, because this is the point that the fins of the rocket first start taking effect, and and they control the rocket, not the launch tower. So if your velocity of the rod is too low, your wings will not have an effect and your rocket will spiral out of control. The apogee is your highest point. The velocity at deployment. Now this is the velocity the rocket will be going when your parachute comes out. Well, we've got a 14-second time delay, and if you look here, OpenRocket is telling us with this optimum delay, it should be 9 seconds. So for this rocket, we'll have to shave 5 seconds off that time delay. So I can go back and show you the simulation on how we'll do that. Then we've got maximum velocity, maximum acceleration. The time your rocket will take to get to apogee, it's only 10 seconds to get to 2,000 feet. Your total flight time, because it's going to take a while to come down, and it's going to take a while because it's going to come down at 8 meters per second. We don't want it coming down any faster than 10. If it comes down faster than 10, you will break something on your rocket. So what we can do now is just go back here. We can double click on the rocket. Now that said it was 9 seconds, so let's just change this to a charge delay of 9, like that. It's made that 9. If we go back to simulate, we run it again, and velocity at deployment, 2.2 meters per second. You're not really going to get it any slower than that, so that is pretty good. So 9 seconds for this rocket will work. I don't think there's much else to talk about other than as we build, we will be adding weight to the rocket, and we'll be adding it in the form of epoxy and paint. There's a few ways you can represent it. I'm going to show you my preferred method. So my preferred method is when we glue in the fins, we weigh the rocket before and we weigh it after. And let's say we've used 15 grams of paint. I don't like to add it to the weight of the fins because the weight of the fins goes into this entire section here. I prefer to add it just to the weight of the motor tube. Some people do add a mass component here and they'll add 15 grams, and that's perfectly fine as well. But I'm happy just to go in here. What I like to do is I like to write in the comments, I'll just say 15 grams of epoxy so I know. And then I go into override and I add another 15 grams to that, and I'll add 35 and do that. And with the paint, I will add it to the mass of the tube and to the mass of the nose cone. It doesn't matter how you represent the masses as long as you do represent them and it's in a logical way as well. For these littler style rockets, it's not that big of a problem, but when you start into larger rockets where you have more epoxy, you do need to accurately represent where it is going to go, because you can see now that weight has dropped my stability and it will continue to drop, hence the reason we said 2.5 when you're designing your rocket. I also like to keep an Excel document of all the original masses of all of my components. That way, sometimes it gets confusing, sometimes you mess up, and I like to keep it as I'm building the rocket. So as I build the inner tube, I will have the masses of the inner tube and the 2 centering rings. Then I will epoxy them, and then I'll weigh it again, and I get the mass then of the epoxy, and I keep all of that on an Excel document. That way, if anything ever goes wrong, you can always go back and you can re-add it later on, or you can also use it to double check yourself if you start getting numbers which just don't make any sense. So I hope this helps. If you have any questions, let me know, and thank you.